I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology, and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and acknowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
Hello guys and welcome back to my channel. In this occasion I'm presenting the Geostatistical Analysis course related to the creation of groundwater flow maps with Kriging Interpolation. We are going to be working with R and Rstudio for the geostatistical analysis and graph design, and with Quantum GIS for the final map edition. We are going to compare the results we get with the Geostatistical Analyst extension of ArcGIS to see how we can get the same results. However, ArcGIS is a private software, but Rstudio and Quantum GIS are open source and free software. I am going to create a series of video tutorials where you are going to learn how to create a Kriging interpolation successfully. Unfortunately, Kriging interpolation is a kind of black box where most of the people just press the button next without understanding what is the math behind the Kriging method. However, in R, there is no button for next. In these tutorials, I am going to explain with examples, step by step, the spatial analysis methodology, where I'm going to be talking about exploratory data analysis, experimental semi-variogram, model semi-variogram, cross-validation, Kriging interpolation, and also at the end we are going to be working with the map edition with Quantum GIS and also reporting results. This is the 7th video of the Geostatistical Analysis course, and the main topic for today is the model semi-variogram. We are going to be talking about the theoretical model semi-variogram and also how we can make the computation of a model fitting for the omnidirectional experimental semi-variogram for different mathematical models like the spherical one, exponential, Gaussian, and also the bezel. We are going to see how we can fit the mathematical model automatically and also manually using Rstudio. And also we are going to see how we can work with the mathematical models in ArcMap. However, at the beginning of the video, we are going to talk a little bit about how we can calculate the directional semi-variograms related with the residuals using ArcMap. Let's go to do it. At the previous video, we worked with the directional experimental semi-variogram in ArcMap. We created a high-resolution grid for the surface interpolation. We interpret the trend removal in 2 dimensions with simple regression analysis models, and we interpret the trend removal in 3 dimensions with multiple regression analysis models. We were talking about how we can get the residual values from our data and how we can plot the omnidirectional and directional semi-variograms associated with the residual values and also the variography. Remember that if you missed that video, you can hit the card located at the top right corner of your screen. Today we are going to be talking about model semi-variogram, we are going to fit a mathematical model in our experimental residual semi-variogram. But first, I would like to talk about how we can calculate the omnidirectional and also the directional semi-variograms related with the residuals with ArcMap. This is a topic that we didn't talk about it at the previous video. Then to calculate the residual semi-variogram, go here, Geostatistical wizard, select your data, Kriging. Next, here we are going to select the ordinary one, and this is the important thing. Now we are going to remove the trend from our data. In this case, we are going to select here the first order polynomial to remove the trend. That is the plane that is going to be removed from our data. Then press next, and here you have to modify the parameters you want. In this case, it's going to be a lag size of 15 meters, and I want 30 lags. The values showing here are related with the residuals. The red dots are the cloud of points, the semi-variogram cloud, and the blue crosses are the omnidirectional semi-variogram, the experimental one. Here we have the variography for the residual values, and here we have the option to select just the cloud of points. The cloud of points is this one, and it's the same that we have here. This one here, and that's the same as this one over here. And for the experimental one, we need the average here, and in our graph is going to be this one. Okay, over here that one is 0. It's the same as you can see. And now we are going to talk about the directional one. Then if you want to see that one, just go here, show search direction, select here true, and then you have to decide what beam angle you want, the azimuth angle for the beam, and also the bandwidth. You can modify this one, and also the tolerance angle. Then for example, for 0 degrees, let's go to check over here what we have. This one, this one. Okay, that's for 0, the orange one. We have something like this one. Okay, let me play with these parameters here to try to have the same. Something like this is not easy because there is no numbers, you know. It makes something like this, go up, go down, up. It's something like this one. This peak is this one over here. Then go down, go up, go down, make something like this. This one is a little bit different. Maybe we can change like this one. Okay, it's something approximately, because we don't have here any option to change the parameters. We can modify here to make this one bigger or smaller, I believe. And also for this one. But we don't have the numbers. Then for example, if we are assuming that this is the angle we want to have. Then for example, this one is for 0 degrees. If we move, for example, 45, something like that. The one we have calculated with Rstudio for 45 is the green one, is this one. Here you have to check here the scale. And then for 90 degrees is going to be something like this one. The 90 degrees here is the blue one. Looks a little bit different. Let me check this one. Okay, it doesn't matter. You have to modify these parameters. And then for 35, 135 is going to be something like that. And that's what we get with Rstudio. 135 is this kind of green. And that's how you can work with ArcMap to calculate the directional semi-variogram with the residuals. And also here you can show the cloud of points according to the direction. If you want to use this experimental semi-variogram with this direction, just leave this direction here and press next after you select what mathematical model you want and etc. Now we know how to calculate the semi-variogram cloud and also the experimental semi-variogram for the residual values, for the directional one and also for the omnidirectional. Now let's go to see how we can fit the mathematical model in our experimental semi-variogram. To make the explanation, I created this graph over here where the title is Theoretical Semi-Variogram Models, and we are going to talk about the three more popular models. They are the spherical, the exponential, and also the Gaussian, and we have here the equation for each of one. Then here for a distance of 0, the value of the theoretical semi-variogram is going to be equal to the nugget. And that makes sense, right? Because as in our semi-variogram, we have here the semi-variance, and here we have the lag distance. H is the distance, right? Then if we have a distance that is 0, we are here. And then the value for the semi-variance is going to be the intersection of our model, is this blue line, with the y-axis. Then it's going to be over here, right? And then that's the reason, because for a distance of 0, the semi-variance is going to be equal to the nugget. Then for a distance between 0 and the range, remember is this distance here. The range is the distance where our data is correlated, and it's also where the semi-variogram model reached the seal, that distance over here, that is the variance. Then we can use this equation over here. When the values, the distance are bigger than the range, then the semi-variance is going to be equal to the seal. Okay, then if the distance is bigger to the range, we are already at the uncorrelated area of the graph, and then the semi-variance is going to be equal to the seal. For the exponential model, for distance equals to 0, the semi-variance is going to be equal to the nugget, is the same as the spherical one, and also is the same for the Gaussian one. Okay, that's the same for the three of them. But here the difference, it's for the rest of the cases where distance is different to 0, we have this equation, and also the same here where the distance is different to 0, we have this equation here. Then there is no a distance between 0 and the range. That only happens at the spherical model. Okay, for these ones is when the distance is different than 0. Let me remove all these ones. The important thing related with this graph is the area where our data is correlated. Then we are going to be focused in this area, and we are going to fit the model for these points over here. It doesn't matter the points how they look like in this area, because this area is the uncorrelated. There is no spatial relation between the data in this area. The relation for the data spatially is at the correlated area of the graph. Then we have to look these points and fit the model according to the points at the correlated area of the graph. Is this area over here. That's the geostatistics. Okay, let's go to talk a little bit about the shape of the theoretical semi-variogram models in this graph. The spherical and the exponential one has pretty similar shape. However, the spherical model has a linear behavior close to the origin, and with the distance, it reaches the seal. The exponential, it's not linear as the spherical one. It's a little bit more curved, and it reaches the seal asymptotically. The Gaussian model is quite different if we compare with the spherical and the exponential one. And the reason is because the Gaussian model with a short distance, the semi-variance, it's pretty constant. It changes just a little bit. And that's the main difference between the Gaussian with the other two models. And also the Gaussian model reaches the seal asymptotically. Now let's go to see how we can fit these three models with our experimental semi-variogram for the residuals using Rstudio. I am going to paste the scripts I created already to calculate the model semi-variogram. Is this section over here. This is the abbreviation that Geostats is using to refer to the exponential. And the same for the spherical, the Gaussian, the Bessel, and just to let you know, there are a lot of different mathematical models that you can use for fitting on your data, but we are going to talk just about these ones. Then the script we are going to use to calculate the different models is the Fit Valuegram. With this script, you can fit the model on your data automatically. Then the parameters you need, first we have to specify what name we want to use to save the information we get. In this case, I'm going to use this one. Then we are going to use this script to calculate the model automatically. And then what we need is the residual for our variogram. In this case, it's going to be the omnidirectional one. And then we have to specify the model that we are going to use. In this case, this is the order that you have to place over here to specify the model. Then what information you need? You need approximately what is going to be your seal, also what model you want to use, the approximately range, and also the approximately nugget. That's an approximately values, okay? And it's something that you have to add here to make easy the iterations for the computation of the model. But what really important I would like to mention is related with the experimental variogram that we are going to use. Okay, I'm going to show you here. This is the directional variograms, but we are not going to use any of these ones. What we are going to use is the average of all of these ones. Then the average is the omnidirectional semi-variogram related with the residuals. We are going to use this one. And I decided to plot all the time all the extension to see how is the structure of the semi-variogram for the residuals, and also when we was working without removing any trend. But now we are going to use just the part of the graph that we need to create our model. In most of the cases, that distance is the half of the total extension of your data, but that is going to depend where the experimental semi-variogram reach the seal, and for each case is going to be different. In this example, we can use the half distance that is going to be around 225 meters over here, and with that set of points from 225 meters to 0 is going to be good enough to create the mathematical model on our data. As you can see here, and as I said previously, the important part for us is the part of the graph where the data is correlated. Then we want to use these points over here to fit our model. Then if we are using all the points to fit our model, maybe our model is going to be a little bit different, right? And we don't want to use all this data because this data is not spatially correlated. And that's the reason, because I want to use just the half of the total extension to have the guarantee that we are covering all the correlated area of the graph. Okay, and that's the reason, because we are going to take 225 meters until here. Then in order to modify this parameter here, we have to go to the script we created the other day related with the experimental semi-variogram for the residuals for the omnidirectional one. It was this section here. And then what we have to modify is the cutoff. Then what we want here is 225 meters, because that distance is the half of the total extension of our area. Then we are going to run this script here to modify the value over here. Okay, then let's see what happened. If we plot this one with 450, let's go to see first this one. That's the one we have saved over here. Then run and plot this one. You are going to see that this one is for the extension of 450 meters. That's the total extension. Now if we change here to 225 and then this one and then plot, now you are going to see that the distance is until 225 meters. Then in this case, we can say that we have a lag distance of 15 meters and we have a total of 15 lags. Then if you multiply 15 by 15, it's going to be 225. Now we can go to calculate the model semi-variogram. First, we are going to calculate for an spherical one, and we are going to run all this script. This script is going to be saved here with this name. Then we can see the values. And as you can see here, we have the model is a spherical one. The nugget, the value for the nugget is 0. You know, the nugget never is going to be 0, right? Because always is going to be a value, because there is a difference between the two samples. But you know, it's really close to 0. Then we have the partial seal, that is going to be this value. And remember that the seal is going to be the nugget plus the partial seal. As we saw here, let me show you. You see seal is the nugget plus the partial seal. And then here we have the range. Then we can plot to see how it looks like the model. Here we have the model. As I said previously, the spherical model reached the seal. Okay, then here we have the seal, and here this value over here we have the range. The range in this case is 91, and it's the value over here. Now let's go to create the model for the exponential one. We have the same variogram related with the residuals, but what we are going to change now is the model. Okay, here we was using a spherical one, now we are going to use the exponential one. And then let's go to run the script. Let's go to see the values. We have these values, and now let's go to plot the model. And here is the model. Then here we have the same. The model is the exponential one. The nugget is very close to 0, and the partial seal is this value over here, and the range is this value over here. Now I'm going to copy and paste this one, and I'm going to talk a little bit about the exponential one, because as you can see, for example, here the range is almost 50 meters, but it doesn't match with the value for the partial seal, right? Because we have 0.18, and if you go to 50 meters over here, you have around 0.12, 13, something like that, and I'm going to explain some things about this graph. let's go here. I prepared the graph already, and as I said, here if you check, the range is almost 50 meters. Then we have to multiply this distance by 3. Then we are going to have a distance close to 150. It's going to be this one. And then if you go here to the graph and then go to the other side, you are going to have the semi-variance for the exponential one. What happened with the exponential one is that it gets the seal but asymptotically. Okay, then the range is going to represent the 95% of the seal. It's not like the spherical one that you get the 100%. In this case, you are going to get just the 95% of the semi-variance. Then if you plot this line over here, you are going to have the real value for the semi-variance, and also the value we get with the range. It's not the real value. It is called effective range, or also practical range. Now let's go to see what happened with the Gaussian model. Let's go to run this script over here. As I said before, now you have to change here the model is going to be for the Gaussian model. Then when you run the script, you are going to see this warning message that is telling you that after 200 iterations, the software cannot compute the model. And it says try different values over here to see if the computer can make the model. But I tried different values and it's still the same. Then what you can do is to fit the model manually. To do that one, I created a different object. It's going to be this one with this name. It's different as this one. And I'm going to use this script to fit the model manually. Then I'm going to say I want a partial seal of 0.17. The model is going to be the Gaussian. I want a range of 40 meters and the nugget is going to be 0. Then let's go to plot this one. And now let's go to see how it looks like. Okay, that's the model fit. Then if you want to change the values, you can change these parameters here. For example, if I put here 50, then you are going to see how the graph change. You see? But I believe 40 is good. But my recommendation is when the computer cannot fit the model, cannot compute the model, it's better not to use this model. You can try with different parameters here to see what happened, but if you still not getting any result, just forget about this model and don't use it. But that's the way, if you want to use the way you can fit the model manually. Now let's go to see another model, just to have another example. That is going to be the vessel model, but I'm not going to talk too much about this model, just to see how it looks like. Let's see the values. And also let's go to plot. Now I'm going to use this script to ask the computer what is the model that fits better with the data I have. Then I'm going to select the exponential, the vessel, and the spherical one. I'm not going to put the Gaussian one because the computer cannot compute this model and it's going to give me an error. Then I'm going to put this one, Fit Valuegrams. This is the script, okay? Then the computer is saying that the best model is the spherical one, as you can see here. And that's the model I believe I want to use for do the Kriging Interpolation. But at the end, the person who is doing the modulation has the final decision. Okay, you can use the model you believe is better for your data. Even if the computer is saying that one is the best, maybe you are thinking it's not the best. Then it's your decision as a professional, right? It's based on your criteria. Also, we are going to do the cross validation, and we are going to calculate the root mean square error. That is going to help us also to decide what is the best model. And also with the maps, we can have a general view of the Kriging Interpolation, and also we can decide what is the best model. Now what I'm going to do, it's I'm going to plot the semi-variogram model with QGplot. But first, what we need is the variogram line model for each of the models. Then is this script. This is for spherical, exponential, and also for the Gaussian too. Then I'm going to run all these scripts. And then I'm going to plot the models with a nice graph. But first, I'm going to fix this one a little bit. Okay, I'm going to run. And that's the final result. What we have here is the model semi-variogram for the three more popular models, that is exponential, Gaussian, and spherical one. Now I'm going to show you how you can select the model you want using ArcMap. Then go here. This option, select the data, go Kriging, next, ordinary, we are going to remove the first order, next, is this plane, next, and here, in this, at the model 1, you can select the type of model you want. As you can see here, we have different models, circular, spherical, and EDC, exponential, Gaussian. There are a lot, right? And the softwares give you by default the stable one, and that's not bad, right? Then if you want to change, you can change. For example, if I want the spherical one, I can choose this one. Also, I can change the range if I want. I can remove the nugget effect if I want to make this one 0. Here I can change the lag distance for 15, and also the number of lags for 15. And then in that way you can get the range, the partial seal, the nugget, and etc. And then when you are happy with your model, you have to press the button next. Even if you want, you can select different direction, as I said previously, with a different bandwidth or even different lag tolerance. Then you can change the azimuth for the beam. Okay, and that's it. Then for one of the videos, we are going to compare the maps we get, the interpolation maps we get with ArcMap and also with Rstudio, to see how similar or different they are, but I'm going to tell you that they are almost the same. That is the end of this video. Thank you very much for watching, and see you on the next one, where we are going to talk about the cross validation, root mean square error, and maybe other things.